Okay, hello everyone. Today we're gonna go look through this final review, and we're gonna do some asymptotic problems to kick it off. So we're asked to give a tight asymptotic bound for mystery search as a function of n, and we have defined n as the size of the array, and we were asked to give the asymptotic runtime bound for the best case, the worst case, and the overall case. And we're also assuming that the array is sorted. And the reason why we assume the array is sorted is because if you look here, like ignoring the rest of the function, we have a function called binary search. And one of the conditions for binary search to work properly is that your array is sorted. And since we're assuming our array is passed in being sorted, that we don't count any n log n runtime or anything. We assume it's been passed in sorted, and we've defined n to be the array dot length, a dot length, since a is our array. So looking at this, we have like a conditional here, and based on the condition, if the random value we generate is less than 0.5, we either do a linear search, which is going to be like some sort of big O of n thing. It could be like searching it for anywhere in the array from first element to last element, and in the worst case, it could be the last element, so it could be linear runtime. But otherwise, we do a binary search, which is going to be on like the order of logarithm. Log n runtime, because we know binary search isn't like log n runtime. But let's go through it a bit more in depth. To think about it, the best case scenario is that like the first element that our linear search that we generate some value, it's less than 0.5. Let's say it's like 0, and like we linear search from element 0, and the first element we check happens to be also have the value 0. So like element 0 has the value 0 in the array A. So we happen to find it in our first case. Then we can just say this is theta of 1. We found it on our first try, and we're good to go. And the worst case is going to be a bit more trickier. So here in the worst case, we're always going to do whichever of these are like worse. So in this case, this condition is obviously worse. So in the worst case, you would get something that's less than 0.5. And you would go in here, and once you go in here, it would be like the worst possible outcome of this. So since this is in big O of n, we could say that the worst case is theta of n. And then for overall, like the best thing we can do to overall bound it is the worst case. And that's why it's big O, not big theta. So like the worst case runtime of this overall function is big O of n, because the biggest factor that contributes is this function called linear search, which is on order of n in the worst case. So overall, the worst thing that like our function can do, an upper bound for our function would be n, because that's upper bounding the entire work that this function does. The function can always be upper bounded by n because of that. Okay, let's go on to 1.2. So here we're asked to give a tight asymptotic bound for convoluted as a function of n, which is the length of the input arrays a and b. So a and b have the same size, and it's n. So n is a dot length, which is also equal to b dot length. They're the same. That is not how you spell length. They're the same value though. So yeah, we're also said if possible, then we want to give a theta bound for the overall runtime. Otherwise, just provide the best and worst case. So looking at this function, we see a lot of stuff going on. We see that first we have an assert statement, and assert statements just make sure that they have the same thing. If this is false, then it will throw an exception. So we're already told that this is going to be true and this takes constant time, so we can just ignore this. And then we look at here. Here we define a new result array of length a dot length. Okay, this is considered to be a constant time operation. But what's really like important is to look here. Even if we like consider this to be a linear time operation, which I guess you could do because this does have a dot length here, so you do need to initialize it of an array of length n. So we could say that since we're doing that, it is that, but we're not actually like changing any values. So for now, like that's not really important. Let's just focus on this for loop, because this for loop is obviously going to give us like the brute of like the function's runtime. So if we look here, it looks like a standard for loop for the outer loop, and for the inner loop, we'll notice that this goes up until here. Like it goes up until I, which is the outer loop. So this in general, this format, whenever you have anything like this, where j goes up until I, is actually on the order of n squared runtime. Because you're like adding up like some constant amount of work from I equals 1 to n. And, well, not constant amount of work, you're adding up linear amount of work. Or not linear, you're adding up I. Because you go up until I. So you start from 0 and then you go to I. So you do 0, from 0 to I, you do 1 work I times, so that's 1 times I. And you do that from I equals 1 to n. Like this thing goes from I equals 0 to n. It's technically, I guess it starts, I equals starts from 0. To be specific. And this summation will be in big theta of n squared. So we know this is on order of n squared, and this operation is constant time, so that makes it nice and everything. We can overall just say that the runtime of this function is theta of n squared. Okay, next we have question 1.3. We're asked to give a tight asymptotic bound for the mystery function. And I wrote the summation because it's going to be useful for this question, but ignore that for now. Let's just look at this question. Okay, so we're given this function mystery. It takes in an input n. If n is 0, returns 0. Otherwise, it returns mystery of n over 3 added 3 times. So like for a generic input n, it's going to break it down into 3 subproblems. We're going to have n over 3, we're going to have another n over 3, and we're going to have a third n over 3. And then each of these n over 3s are going to break it down into more. So we have n over 3 as our new n, and then we're dividing that by 3 again. So this is going to be n over 9. So we're going to have like this n over 9 3 times. And like this is going to repeat 3 more times, like for here, and 3 more times for this middle branch, if I can even fit it in. Yeah, so like this will branch off, this will branch off. And you can see like it goes like decently fast, but like the question is, when does this stop? Because that depends on the value of n, right? We stop when we get to 0. And when we're doing this division, this is integer division. So eventually we'll get to something that's like 2 over 3 or 1 over 3. And both of these in Java, like when we do these will both go to 0 because this takes in an integer, right? And we're doing integer division. We're not dividing by like 3.0 or something. So we know we're going to get 3 Yeah, so it will eventually hit this base case and stop the recursion. So we just need to like figure out until we get there. And we know that is going to be like the height of this tree, like how long we go for. The height is going to equal log base 3 of n. And that's like the same as a general tree, except for now we have like this third extra branch, which adds that log base 3 of n factor. So in here, how much work do we do at each level? Well, here at the first level, like we enter in here, we have like our first function call, and we basically do like this one bit of work, like checking if n is 0, and that's like constant amount of work. So we do like constant amount of work at like value n. So constant work there. Then we branch off into 3 different stuff. So we do 3 calls. So we do 3, and I'm going to write it as 3 to the power of 1. You'll see why in a second. Three calls. Then I go here, and like for this one, I do 3 more calls, but I also did 3 calls for here, and I also did 3 calls for here. So in total, on the next level, I did 9 calls, which I'm also going to write as 3 squared. And if you draw this out again, you'll have like 3 here, 3 here, that's 6, then 9, 12, 15, 18, 21, 24, 27. And 27 is actually 3 to the power of 3. I can even rewrite this 1 to be 3 to the 0. And in general, this is going to be like it's going to be a summation from like I equals 0 to, and we're going to add this up all the way up until, when are we going to stop? What's the height of the tree? We're going to go all the way up until the height of the tree, 3 to the power of the height of the tree to be precise. So like 3 to the h, or 3 to the log base 3 of n. And when you have 3 to the log base 3 of n, that's just n, right? And that makes sense because as soon as you add it up, that you're branching to n, like that means you've hit a base case. You're going to be hitting the base case. It's constant amount of work. We're done. So we're going to be summing up until log base 3 of n. And what are we summing up? We're summing up 3 to the power of I. And I guess I really should write this just to make the pattern like explicitly clear, log base 3 of n. And we're summing 3 to the power of I. That I could also have been made a bit more clear. And if we plug that into this formula, we can see that our total sum is going to be like just putting in this formula, we could say a sub 1 is just 1. So it's going to be 1 times 3 to the I. And we'll notice that gives us 1 times 1 minus r is 3 to the, and then n here is log base 3 of n. And that's all over 1 minus 3, which is just negative 2. So I guess I can factor out the negative 1/2 here. And then 3 to the power of log 3n is just going to be n. So we have 1 minus n, and this ends up being n minus 1 over 2. So what's really important here is that this is on the order of linear. We can use big theta bound for it. And we could say that this overall is like doing like linear amount of work. Okay, and for 1.4, let's move on. We're asked to give an asymptotic bound for debug binary search as a function of n, where n is defined as the length of the input array A. And we're asked to give a big theta bound for either the overall runtime if possible, otherwise like for the best and worst case scenarios. So let's get into it. This looks like a standard binary search algorithm. So if we look just with like some debugging stuff attached to it, so we can like figure out like, is this code working? The first thing we do is we find the midpoint of our start and end. This code what this code is doing, it's doing end minus start over 2 plus start. And if you like make a common denominator, if you multiply this by 2 over 2, now these have the same denominator. And since these two things have the same denominator, you can just put them on one thing. Just get rid of this, extend this over. And here we have minus start plus 2 start. So that's going to give us end plus start over 2. And I prefer to write it as start plus end over 2. And we can see that this is clearly like giving the average. Like if you add up the start and the end and then you divide by 2, you're going to get the average. So that gives us the midpoint between these. We're getting the mid. And then we basically see if our middle index is equal to the target value we're looking for. If it is, return true. We found it. We found that the thing works. That the index exists. That the value exists. The target value exists. So then what we can do is, if we haven't found it, if we entered the else if, then we could say, is it on the left hand side or is it well, if here, like, let's say we have like some array, we have start here, we have end here, and we have like mid in the middle, and then let's say it wasn't the middle value, so it wasn't here. Then we say it was the value here, since we know it to be sorted, is like the input here less than the target. So if this value, like let's say this was like 7, and let's say the thing we're looking for is like 16. So if if 7 is less than 16 is true, then that means that 16 is going to be like somewhere here, right? It's going to be in the right half. It's going to be to the right of this. So what we're going to do is we're going to move start over to m plus 1. We already said it's not m. M is 7. So it's going to be like 16. So it's going to be somewhere here. So then we move it to the next thing over, and we're like, okay, like 16, we'll find out. Then we put mid to here. Then we'll move start over here, and then eventually we'll keep on getting it until mid's there. Obviously, if it was something like, let's say it wasn't 16 we're looking for, let's say we're looking for 4, then it would go into the else, and it would move n to mid minus 1, right? So we know it's not 7, so we know it's like here. And start would, of course, have been here then. We can just keep on like binary searching, cutting our space in half until we find it. So this is like generally a logarithmic time algorithm because you're like cutting in half at each step of the way. But if we look here, the debugging stuff we added is actually going from start to end. So like in our array, no matter which case you did, if you let's say I can do it in both cases, and I'll show how both cases come to the same result. Let's say we go into this case. If we go through this case, then we come in here, and start is index n over 2 plus 1, and this is at index n minus 1, I guess. So then what we're going to do is we're going to iterate from index start to n and do like a constant amount of work. But when we're iterating from n over 2 to n, this is we do n over 2 iterations when we go through all of these. We do n over 2 plus 1, n over 2 plus 3, n over 2 plus 4, all the way up until n. When we do that, we do n over 2 work, which means this thing is doing order of n work. So this thing is doing like order of n work, and let's say we went into here, and instead of doing start to mid plus 1, we did end equals mid minus 1. So now if we put it here, we'll notice that we still have n over 2 work that we're going to do, right? From start to m, we're going to print out all of these. We're going to print out this, until we get to n. And that is n over 2 work, which is in big O of n. So we're doing actually linear work on a logarithmic time algorithm just by adding this debugging code. And that's why you probably don't want to have debugging code in like actual like time sensitive code. If you're doing timing stuff, you'd probably want to have that like before debugging, just to make sure your debugging time stuff is accurate, you know? So since this is, we have something here that's doing linear runtime, we can say in the worst case, this is like actually linear runtime. And in the best case, we could say that we actually just found it. Let's say the thing we were looking for was like 7. It was in the middle, like, which happens to, let's say like 7 was the value in the, like, let's say we had like 1, 3, 7, 8, 9. I don't know. This is a sorted array. Yeah, this, like, we can do binary search here for sure. And let's say we were like looking for 7. We'll say right away, is the middle element 7? True. And then we return. We're done. And that's constant work. And a common misconception that comes here is people are like, what if we only had an array of size 1 and we only had one element in it? Or like, let's say the element was like 7 here, and then we called it on 7 and we got it here. This is actually not a good reason for why the answer is bounded in theta of 1. And that's because when we're looking at asymptotic behavior, we're looking as n goes to infinity. We're looking at like the size of our input, the length of our input array A goes to infinity. And if we're taking a limit of that to infinity, if we're looking at like large input sizes, we can't just choose a specific size and say that that makes it theta of 1. Otherwise, you could say everything is like theta of 1. By that logic, what we're really looking for is like, is there like some specific behavior of the function that could allow us in the best case to just be done with a constant amount of work? And there is, and that is that case if the first element we happen to choose is here. And this you could have like a million elements. You could have like more elements here, you could have more elements here, you could have infinitely many. But if like the first element you choose is it, that's like good to go. You would be done in constant time. Okay, let's move on to question 1.5. So for 1.5, we're asked to give a tight asymptotic bound for many n as a function of n and m. Okay, so generally when they say to put it in terms of two things, our bound is going to use like both of those. And it says the same instructions as before. So let's like dig into this function. If n equals 0, then we return 1. Otherwise, we add to like some variable k the result of calling many m times. We call it from 0 to m. So we call it on order of m times. And what we end up doing is first we start out with m. And the only thing that we really reduce, like m is always the same, right? What we reduce is n minus 1. So we call this m times, so we're just going to grow out. And you're going to have like m, your branching factor is going to be m. You're going to have like m branches. And n minus 1, each of these are all going to have like m minus 1. All of these are m minus 1. And then all of these are going to branch out with like m minus 2. And all the way up until you go to 0. So like obviously the height of the tree, if you had to say something, like the height here is n, then m minus 1, m minus 2, and then it's like dot dot dot. And eventually you get to like some tree branch which has 0. So you could say that the height, or I guess just to make it neater, I'll say like height is going to be equal to, since we go n, m minus 1, m minus 2, it's just n. We have height m for the tree. And what is the runtime of each node? Well, each of these nodes, they all have to make m calls, right? They have to make m recursive calls. So they do a for loop that's like obviously of like if you have a for loop from I equals 0 to I is less than or equal to m, this is going to be big O of m. So the runtime in each function is m. And m is never changing. We always like pass in the same n, so it's the same n, and we always have the same branching factor. So the branching factor is always going to be m, because we always do the for loop m times, or like order of m times. So then what we can do is we can use one of these formulas that I wrote out in this corner here. So if we have a recursive function, there are two things we can do. And the formula we use depends on like if the work per node is the same for all nodes in the tree, or if the work per level is the same for all levels in the tree. So think about like which of those do we have here? If you think about it, like each level is clearly doing like different work, right? So the work per level is not the same. So we can't really use the second thing. So here we're going to have to use the first formula. So for the first formula, is the work per node the same? Well, the work per node is the same. They're always doing m work. They're always just having a branching factor of m. So we know that the work per node is always this thing is always going to be m. And we're going to multiply it by the number of nodes. Well, what's the number of nodes we have? So here we have one node, then we have m nodes, then we have m times m nodes, which is m squared nodes, then m cubed nodes, all the way up to m to the power of n nodes. An alternate way to do this is you can notice that like the first level is doing m work, and like here I'm just gonna say these all have m because they're all doing m work, so I'll just write m. And like how much like work, what their runtime is like what's really important. So here, since they're all like m work, here let me just clean this up a bit. Yeah, since they're all doing like m work, what we can do is we can say that the first level is doing m work and the second level is doing m times m, because we're doing m work m times. We have m nodes, right? We have a branching factor of m. Each of them are doing m work, so we're doing m plus m squared. And then you can like kind of see if you draw it out another level, you have m here. Each of them are doing m work, so that's going to be m squared. And you have m squared here, you have m squared here, you have m squared m times, that's m cubed work, right? That's going to be m cubed, then m fourth, all the way up until the height of the tree. We just do this for every level of the tree until we get to the height of the tree. And the height of the tree is m. So we go all the way up until n. And what we'll notice is that like the biggest factor here, the dominating term, is m to the power of n. So we can actually tightly bound this in big theta of m to the n. Okay, the final stretch. Here we're asked to give a tight asymptotic bound for skip as a function of m. If possible, give a theta bound for the overall runtime. Otherwise, provide a theta bound for the best case and the worst case runtime. So here we're told that if n is less than or equal to 1, that's when we end our function. Otherwise, we call skip with n over n. And n over n is always going to be 1. And so this is equivalent to skip of 1. And then we call skip of m over 2. And something interesting to note here actually is that skip of 1, if we call skip with 1, it says 1 is less than or equal to 1. This is true, so that we're just going to return. So this is, we can actually ignore this as just like constant work. We can call this constant work because you always finish after this. Right after this you finish. So what's really happening is you're just calling skip of n over 2. So we can draw out our tree, right? We're always doing constant work. And we always just branch out with n over 2. And we're always just doing constant work, right? So, and we just like branch out until our final constant work. So here we start out with n, then here we have n over 2, then here we have n over 4, all the way up until we get to 1. And this is like the value of n, and this is the work. So what we can notice here is that if we think about this, we're dividing by 2 each time. So what is the height of this tree going to be? We're dividing n by 2. So how many times will we go on dividing by n by 2? How many times do you need to divide n by 2 until you get to 1? Well, the height is going to be equal to log base 2 of n, or just log n. And sometimes log base 2 is just denoted as lg of n. So here, since we have log base n of the levels, and we do 1 work at each level, we can use this formula like here, right? We have log n levels, and we do 1 work at each of them, so it's log n times 1, and this is just going to be theta bound of log n, or LGN if you prefer. Both of these are the same thing. They both just mean log base 2 of n. But here it's like the base doesn't really matter, though that is what is being the asymptotic bound for this function. So hopefully that made sense. If that didn't, feel free to comment below. And since the overall height of the tree is log n, that was like the really hard part to realizing this question. So hopefully this ended it on a good note for you, realizing that this was like constant work, the skip of n over n, and catch y'all in the next one.